sometimes I have some topics that I would like to share with you, and they are not a tutorial per se. It's not something that I can teach you, but I can share some of my knowledge or some thoughts that I have with you, and hopefully you can contribute or help me to improve my knowledge as well. And this time I would like to talk about speeding up Grasshopper. And a couple of days ago, I published this document that I'm showing you right now, and I asked you guys at the Facebook group to contribute, to share your experience with speeding up Grasshopper, and it actually works really nicely. The community works. Many of you have contributed, and I see that somebody's right now adding some more notes into the document. So here I would like to go step by step, telling you what is my experience in speeding up Grasshopper. This is by no means everything that you can do to make things faster, and maybe sometimes I might not be even right, but some of these suggestions seem to be best practices to me. It seems like something to do to make your Grasshopper definitions run nicer. I also tried to test all the suggestions that I have here. Some of them are actually documented in the pictures. By the way, you can find the document in the description of this video, and you can even see it now that it's something is happening there, and you can add more things. I tested most of these things. Some of them I haven't, and therefore they are either dubious or some of them proved to be wrong, so I crossed them out. But never mind. Those that actually work, I've left in the list, and also if they were suggested by somebody else, I also wrote down or pointed out the name of the person who made the suggestion. And I know that here on Facebook you cannot see my screen in full resolution, so I will take it into consideration. I'm looking at the second screen and I see basically what you see. So thanks to that, I can adjust the size of the components on the screen to make things look bigger. So I will try to keep it like this, and I will go step by step, telling you what you can do to speed up your Grasshopper, or maybe you can have some comments on what I say. Also, this is going to be I will try to provide you with a full-fledged information. So this is not a teaser to one of our other tutorials that we might have on our website. I'm pretty sure you know the research website, which is rese-arc.org, and you can find some commercial paid tutorials here that we made with a lot of other tutors, some of which I see are watching today, so hello. Anyway, some of the topics are quite long, and I might make a standalone tutorial just to cover those topics, but by no means this is a teaser. I will try to give you as much information as I can. So let's start. Anytime you want to comment on whatever I say, just write it into the comments of this video, so that I can react to that. So I divided the suggestions into some groups, and the first one is a systemic approach. So what can you do systematically to improve the speed of your Grasshopper definition? So first of all, I think that you should be using Rhino 6, and there are two reasons. So the first one is whenever there is an update that might improve the performance, it's definitely going to be for Rhino 6 and not for Rhino 5. That's one reason. Another reason is that some of the components now in Rhino 6 can be processed on more CPU cores, and you can actually find those components just by placing them on the canvas. And those that work in parallel, they have like little two dots up here, and I was kind of sure that this one works as a parallel component, and it doesn't. So I actually don't know by heart which ones are those, but some of the components they can run faster because they can utilize more cores of your CPU. Now I see that none of these actually works in parallel, but maybe over the time I will find some. I don't remember exactly. Maybe you do know which ones. Usually they are those that do some simple operations on a list. I thought that it might be either sort, maybe not really sort, but multiplication and addition could be those, but it seems like it's not. So maybe move. Never mind. In my experience, it doesn't really make much difference if the component is parallel or not. They're still more or less the same speed, at least to my experience. But whenever there is the component, you don't have to do anything. When it has those little two dots here, they run on multiple CPU cores, and there is a good chance that they will actually run faster than the old ones. So my first suggestion is use Rhino 6. Also, sometimes it's useful to make some hardware upgrades to your computer to make your Rhino and mainly Grasshopper run faster. So, but not all of the upgrades are meaningful, and that's the most important thing. Back in the past, many architects thought that they need to have a good graphics card to run their software really fast, but it's not. Usually, it wasn't the case. Because most of the software never used the graphics card power. Today it's different. It's good to have a neat graphics card, but not for Rhino, not for Grasshopper. You should have something that is something above the built-in graphics card, but don't spend too much money. Also, to have a 16-core CPU doesn't really have much sense because most of the Grasshopper still runs on a single thread, single core. So it's much more meaningful to have a computer that is fast in single core than multi-core super fast computer. So mainly the AMD CPUs today, they have multiple cores. They are super fast in parallel computation, but they are not so fast as the Intel CPUs currently. Also, when it comes to the memory, on a single core. Also, when it comes to the memory, if you are working with large files, it's good to have a lot of memory. But if you do everything right in Grasshopper, you don't spend so much memory. So if you see that your definition is exceeding 8 gigabytes or 16 gigabytes even, it's probably something wrong with your definition, not with your computer. So upgrading your computer means that you run out of memory later, but eventually you will run out of memory anyway. So upgrading your memory only because your Grasshopper is using all of it doesn't really make much sense. But still, it's good to have a lot of memory. Graphics card, as I said, it's good to have it because then the rendering also on the canvas here and also in the Rhino viewport that can run faster on a good GPU, but still it doesn't really make much of a difference. If you have any graphics card, it's still good. Now, some of you suggested that some of the components that work on multiple cores is one of them is, for example, area. So yeah. So the two dots are not on the right side, they're on the left side. So when they have something like this here, they can run on multiple cores. So only the components that have this, those can utilize or use the multi-core CPU that you might have. The other ones, they don't. Another one should be divide curve. Let's see. Yeah, that one as well. So these should run faster in Rhino 6 than they used to run in Rhino 5. Eventually, I think that most of the components will be like this, or those that make sense. We'll come to it later on the list. We also have some tips for coding in Grasshopper. A very important thing is the next point, turn on profiler widget. That's not turned on by default, so let's see the area, or maybe even divide once again. So let's pretend that we have a curve here somewhere. I will just put it here. All right. So I will draw a curve like this. I will reference it here like this. And let's divide it. Okay. We can even measure the area, which doesn't work, but maybe we can close the curve. So close curve. Yeah, now it also shows the area. Why doesn't it show the profiler? That's strange. Alright, so I made a suggestion that you should run a profiler and it stopped working for me. Anyway, where do you find the profiler? It's here in Display, Canvas Widgets. And I actually don't use any of these, they are always on. But one that actually is very helpful is this profiler. When you switch it on, most of the components here, let's just make it a little slower so that the computer has something to do. Maybe then it shows the bubbles of the profiler. Let's see. That's funny. It doesn't really show them anymore. But just a moment ago, they were there. And if this is something with a screencast, then we might have a little bit of a problem because that's something that we are going to use a lot. Let's start a new definition. I think it's some problem with the rendering here on my computer while I'm broadcasting. So let's see, set one curve, divide curve. Let's do it into 500. Yeah, and it doesn't really show the profiler. So I will switch it off, switch it on. All right, so in this case, I'll try to restart my computer, but actually just Rhino, don't worry. And I will show you how does it look on the screenshots that I've made before. So I will just switch off Rhino and switch it on again. So if you look at all the screenshots that I put into the document that I shared with you, there are little bubbles underneath most of the components. Not all of them, but most of them, they already have a bubble. And this bubble tells you how long does it take to compute that specific component. And that's not something that you cannot really change the number, but it basically tells you which component is actually slow in your definition. So here you see that the random was pretty fast, it's just 14 milliseconds, and it's white, so it doesn't mean anything. But some are yellowish, green, something a little bit more, it attracts more attention. And these two, both of them took 3.1 seconds, which is a lot. And then this took 4.1. This is the most red component here. And I know that these three actually took a lot of time to calculate, to compute, so this definition was being calculated for at least 10 seconds. So now I know that if I want to speed something up, then I need to focus on these three components. And again, I'm looking at the Facebook feed, and Nader is saying that the profiles will not appear if the component is too fast to measure the time it takes. Yeah, that's why actually I slowed everything down a bit, but still, maybe it was too fast. Let's try once again. But this is an essential tool to tell you where do you need to improve your definition. If it's too slow, then it has to be made faster on the components that actually prove to be the slow ones. So let me try once again. Maybe this time. You see, now, even though this runs really fast, it shows the profile here. So I know that just referencing the curve from Rhino to Grasshopper, it took 7 milliseconds. And it's the slowest component of all, and that's why it's red. And I zoom it in a little bit more. Now I should divide the curve. And even without doing anything, this takes 10 milliseconds. So now this one is the slowest one. And now let's try, I'll just plug this in, and now it takes 23 milliseconds. And if I divide the curve into 500 pieces. Now it's 9 milliseconds as well. Um, okay, that's super fast. That's also nice. My computer is also not the slowest one of all of them, but still. Um, let's duplicate the data and let's make 100 of such curves, which should itself take some time. It doesn't really show. And now when I divide it, it's 85 milliseconds. So because I created 96,000 points. So this is good to know, and this is kind of essential for you to know which components are slow so that you can optimize them better. So keep the profiler on all the time. This is what I do. It's actually quite a nice tool to nice hint for you to know which is the heavy part of your definition, which one is not really. I'm going to keep it on. I will hope that it remains on throughout this video because we are going to refer to it a lot. Okay. Another tip is turn on autosave, because if something goes wrong, at least you will have the autosave on, but only do it if it makes sense. Now, why is that? Let me just show you where to do it. Here, Files, Enable Autosave. My autosave is off because probably I was working with large files. And how does it happen that a Grasshopper file is large? It's usually not, because it's just a set of instructions and the data usually comes from Rhino. But sometimes you can internalize the data, which means that when you save the file, so let me just save this file, save document, and I will just put it on my desktop so that I will call it 01. And this is just a couple of instructions, so it doesn't contain any data because all the data is being referenced from the computer. And it's being calculated, so it takes some time to calculate the data. And now the file itself is not so big. I'm not really sure if you can see it, but it's 8 kilobytes on the disk. This tells me. So it's a small file, but if I keep the data inside of the file, which I do by internalizing, so I will just I will show you this again later on. If I place the data here and I say internalize data, and I can even delete this, now all the points that I created are stored in this PT component or parameter. All the data is then stored in the Grasshopper file. And now it became really slow. It's even slow to even do anything, so my computer is freezing now. So I will save this file, save document as 02. And now let's see how big it is on the disk. And it's already 1.66 megabytes. And that's a lot for a Grasshopper file. And you see here that even rendering takes a long time because you can maybe this is because the points are possible to move in the viewport. That's why it's slow. But still, if you internalize a lot of data and you keep it in the Grasshopper file, then even saving the file takes a long time. So you don't want to keep the autosave on if the file saves too long, because if it's each 5 minutes, then each 5 minutes your computer freezes for a couple of seconds, and it becomes really annoying. In case your autosave is off, then be sure that you keep saving your file very often, because otherwise you can lose all your data. And as you see, in my case, I keep the autosave off because I hope that I will not make such a mistake that will destroy my file. And also I keep saving the file very, very often. And this is a rule of thumb. Always save the file before you do something dangerous, which in the case of Grasshopper is basically everything. Whatever you do might be eventually dangerous. So I'll try to delete this component here. My Grasshopper is now slow. This is exactly what we are trying to avoid, but anyway. This brings me to another point. Now it should be faster. Another point is use the solver lock, but do it carefully. This is the solver lock. When you press the middle button, or if you right click anywhere on the canvas, you can lock the solver, which means that whatever you have on the canvas, it's just passive, it's not being recomputed. When you lock the solver, it's just something that you can create, you can work on that, but it's not being calculated. So I can reference the curve here, this one, just referencing it, and you see nothing happened. Then I can say divide, and I connect it here, and nothing happened. I need to unlock it, and then it recomputes. But I wrote into this document, use it carefully. Locking the document is not a problem. It's never a problem because it always releases the computation power for something more meaningful, and this is not being calculated. No matter how difficult it is to compute, how long does it take, it doesn't ever recompute. So it's always fast. You can make any changes here. If your definition becomes slow, just lock it. You can make any change. But the dangerous moment is when you unlock it, because if you do something wrong, you cannot really see it here because this is not being recalculated, so you don't see the difference. So, for example, if originally this is dividing the curve into 10 segments, and I can change it to 50, for example. When I plug it in, I don't see the result because it's not being recomputed. When I unlock it, it recomputes and it's done. The very dangerous thing is that if now it's locked and I don't see what is happening, and if I say that I want to divide it into 5 million divisions, I'm pretty sure when I plug it in, it's locked, nothing happens. When I unlock it, this probably freezes my computer. I'm going to risk it now, and let's see. Yeah, so it's not responding. It's not doing anything. When this happens, you can try to hit the escape key as many times as you can. So this is something that I'm going to do right now. And then what happens is this error message. So sometimes your Grasshopper just freezes on its own. It knows that something is going wrong, something is taking too much time. This happens also when you hit the escape key. If this happens, the Grasshopper actually locks itself until you make any change. So now if I change this, it unlocks and keeps running. And this is quite a dangerous moment, but it's good when it happens because now you have a chance to lock your solver and you have the freedom to actually make any change you want, because if I did this without locking the definition, it's going to slow down my computer again, and it's not really going to help much. So I changed this huge number to something more meaningful. Even 86,000 is a lot, but it's not going to take so long. So it's only 320 milliseconds in my case. So that's why you should be using the solver lock very carefully. So it's not the locking that is dangerous, it's the unlocking that is dangerous. Generally speaking, I should actually say, why is Grasshopper actually so slow? It's in comparison with other programming languages, like the full-fledged programming languages as C++ or even comparing to Java, Grasshopper is very slow. But there are two very, very good reasons why it is slow. One reason is that Grasshopper as a programming language is using something. It's based on a paradigm that is called functional programming, but it's not really the main thing. But the main thing is that it's using the immutability of data. So what I mean is that no data can be actually changed. Whenever you make a change, you also make a copy of the data. So, for example, if I reference the curve that we have here, so now this is the reference of the curve, and when I move it, what happens is, and let's do it like this. Alright, so there is another curve. So the first curve remains and the second curve appears here. So this is called immutability. Instead of moving the existing geometry, it creates a copy of the geometry. So each pipe here or each wire here basically contains a copy of the data that it's passing from one component to another, which means that it also consumes a lot of memory, but also the mere operation of copying the data takes some time. So this is something that makes Grasshopper really slow. But it's very safe. Using immutability even outside of Grasshopper is very useful, and it's a smart thing to do. The only problem is that it slows down your computer. The good part is that you never destroy the existing data. So whenever you keep the data, whenever you have nice data here, you don't destroy it by moving the data. I haven't been using Dynamo in Revit for a long time. I tried it when it was new, and I thought that they got it all wrong because it wasn't using immutability. It was mutating the data. So whenever you run, back in the day, maybe it has changed. Whenever I was running a Dynamo definition or a script, it changed the data. So it destroyed the original data. Grasshopper doesn't do it. And I think it's right. I think David Rutten got it completely right. This is the right thing to do, but it compromises the performance. So it's slowing down the computer. Another good thing is it's not only not destroying data, but also this is a prerequisite. This is a must if you want to do parallel computation. So if we are using the area that can be computed on multiple cores, this is a must. You need to have immutable data. You cannot change the data, because how parallel computation works is it actually splits a list of data into chunks and makes an operation on the chunks, and then it connects it together. And it means that the data cannot change under your hand while it's split into the chunks and being computed on multiple cores or processes. So it's a very good thing that Grasshopper is immutable, but it's slow. Another reason why it's slow is that it's actually each component actually really creates the data that it's processing. In some other programming languages, you can fake creating the data. So, for example, let me show you what I mean. If I click here, I can see that it contains some data. If I click here, I can see that it contains some other data. But I'm not using this. Well, I'm actually using this data twice. So it has to actually exist. But if I'm again, for example, moving this central point, this data doesn't actually have to exist, only this data needs to exist. So some programming languages, they are somehow faking the immutability or optimizing it by not really making all the data immutable, but only those data that needs to be actually calculated is being calculated, other ones are not. So this data in some optimized programming language would never exist, and this would be mutated or changed by moving, and it will save some memory, and also it will save some time. In Grasshopper it's not possible because you need to check what kind of data is inside. So I need to be able to hover my mouse cursor here and see that this contains a point. So all the data coming out of the components, they need to actually exist. So this spends some memory, and this also spends some computation. But this is really good because you're building up your definition, you're building up your script, and you need to have a feedback whether the data that you're producing is valid or not. In this case, I see that it's valid, and also, well, that slows down your computer. But it's a good thing. It's a good thing that it does it, and otherwise we wouldn't be able to use Grasshopper the way we use it. I'm now looking at your comments. And Daniel says, in my experience, Dynamo in Revit is super slow comparing to Grasshopper, and Nader doesn't believe. I don't know. I'm not using it. I only tried it once because I thought finally somebody is making a competition for Grasshopper, and at that time when it was new, I thought that they got it all wrong, so I never used it again. Sorry, I took a sip of water. Okay, let's see another point that I have here, because I think I'm actually quite slow. I reserved 2 hours for this video, but I think it's too long, and probably we should speed up a little bit. So, Now let's skip the reduce file readings and let's go to internalizing data. This is something that I've done before, and I told you that it's slowing down basically your save time, and sometimes it's not a good idea, but sometimes it is a good idea. If you have a really long definition, so you have 100 components that calculate something, and there is when your definition looks like something big is here, then it comes to a bottleneck to one component only, and then you've got another part of the definition here, and then it again there is another bottleneck, and it means that you basically create, those are some separate modules, you can think of them as that. You end up with certain data, and that data can be, well, at these points, at the bottlenecks, your definition could be split into more definitions. So if it becomes really slow, just internalize the data when it makes some sense, when the data is already somehow processed, start a new definition, place the internalized data there, and make another part of the computation there. This might help you by not recalculating those parts that are already good and done, and this is something that is quite useful. I used it recently. I can actually show you a definition that I made, and it's an ugly one, and actually very slow, and I made a lot of mistakes there. But I will show you anyway, because eventually it was quite useful. That's something that I was showing on Facebook recently, but I'm not really sure where did I put the file. Yeah, this. Well, maybe this might be it. This is a different one, but still, let me show you. This is a huge definition. It's not a nice definition, but never mind. Never mind. But I want to show you another file. Let's see this one. Also not this one. But you see that I could somehow use the bottlenecks here. Maybe I could split the definition here, split it here, split it here. If I didn't have all the wires here. But again, this is not a good example. This is really a bad example. This is something you shouldn't be doing. But I'm looking for one part in particular. And that might be the file readings somewhere here. Not really. Yeah, let's see here. Okay, yeah. This is it. I will just lock it, or I'm just going to make it stop whenever I turn on the lock, like release the lock. When I release the lock, you see that it takes a long time to calculate, even though it's quite slow. But here I realized that at the beginning, okay, it even disappeared. So yeah. So here at the beginning, there are some file readings that are eventually not so slow. But then I converted the data somehow, and it's becoming a bit more slow, and there is a lot of data processing that comes from some files that I have on my hard drive. And the file readings are usually quite slow, and the processing and parsing of the data, because when you read a file, it's basically a list of texts or strings, and then you parse them or change them into integers, and this takes time, and it's kind of slow. Eventually you end up with processed files, and if you do it just once, for me these are configuration files. Those files never change. So what I did, this is the first version of the definition that I was having. So I knew that this part actually takes a long time. So in the new versions of the definition, which is for example this one, no, not this one. It should be maybe this one. Yeah. So I have internalized some data here. Well, that's not really the case, but we can pretend. So there are some internalized data here that has been pre-processed once, and for me it doesn't really make any difference, because if my files on the disk are configuration files, then I know that when I change them on the disk, I can reference them again, and then internalize the data. And I can do the processing only once. So that's why it's good to internalize the data and reduce the file readings. Because if you read something from your hard drive, there is a good chance that that's data that is changing slowly, and you know when does it change. So just change them manually, internalize when they are processed, and then never process them again. Only process them when you change the data on your hard drive. This is something that I already told you. Break into smaller definitions when it makes sense. When you know that, for example, this is an obvious bottleneck, I could split the definition here somehow, and this could be the first part, this could be the second part. If this computes well, then I can internalize the data here, put it into a new definition, and then process it in a new definition, and never come back to this one again, because then it might be faster. In my case, I'm using a lot of anemone, or anemone if you want, which is a looping plugin by Mateusz Wierzicki. And that also, you can make a lot of mistakes there using more of the anemone couples, and I will show you later on. If you split your definition with more anemone couples or anemone loops, there is a lower risk of actually losing some performance. So split your definition if you can by internalizing data. Now somebody already during this video, Aitor actually wrote that you can loop the list with Python or C#. I'm going to refer to that later on. Avoid Boolean operations if possible. I don't know. I don't really know. But I think avoiding Boolean operations, by that he means that the geometrical Boolean operations, like you have two volumes and you want to make a Boolean union or Boolean subtraction. I don't know. Sometimes you need to use them. I personally don't use them because I never need them. But this is something that appeared here only now, and I didn't have a chance to check whether this actually, if it's proven that this slows or speeds up your definition. Let me now close all of these, and let's continue with my other suggestions. The other group is more specific, and it refers to rendering of the canvas, which is the Grasshopper itself, and it also refers to rendering in the Rhino viewport. So disabling preview might be a good idea, because whenever you are viewing anything in Rhino, if it's a NURBS object, so for example like sphere, let me unlock. So there is the sphere. It always has to be converted from NURBS into a mesh object. So it's always meshing the breps and NURBS. I'm just going to check. Yeah, okay. So whenever you want to display something like this, there has to be a conversion from the brep or a polysurface into a mesh, so that your computer can actually display it. So if you disable the preview, you might save some computation time. So it might be faster to work with this, because the viewport doesn't have much work with displaying your data. That's one thing. This is something that is quite obvious, but for me, great surprise was actually the panel component. So it's this one. It's a component where you can actually write stuff, but you can also read stuff from somewhere. And recently I was processing really large data, so it was hundreds of thousands of lines of text, or maybe millions. Actually, when you want to check what is inside, when you hover here, it actually shows you only some. Let's make a list. Let's make series. So when I hover here, well, this is too short, so let's make it much longer, like this. So now you see that this contains 100 components, and you only see the first 10 and the last one. So it basically only displays 11 components. But when I plug it here, it actually needs to render all the values here. Rendering 100 values is not a problem, but rendering a million of values, let's see 10,000 values. It's not a problem to display to calculate it. It doesn't even show the bubble here, but it's a problem to display it. Now this component is really slow. So 10,000 was not enough. Let's do 100,000. Now you see that it's 200 milliseconds. Let's make 1 million. It's going to be even slower. Now my Grasshopper is freezing. So it's 2.3 seconds just to display the content of this. And creating the content is 10 milliseconds. So be very careful with using the panels, because sometimes if you're working with large data, it actually slows down everything significantly. And also, this might not only happen if you're using, if you're having large data, but sometimes if you make some mistake, and just by mistake you create a lot of unnecessary data, and if you display it in a panel, it slows down everything even more than it was before. I'm going to refer to actually slowing, creating wrong data later on. But this is another good observation, that don't use the panels if you don't have to, and certainly don't use them if you have too much data. Then I got two suggestions from Myron, and I tested them, and they didn't prove to be correct, or maybe I made some sort of mistake, or maybe I misunderstood. So, but I'm going to tell you anyway. You can try that. He says baking into turned off layer speeds up baking. So I tested. So I made two layers. One was visible, one was hidden. It was also their name. They actually were visible and hidden. And I tested baking using a human plugin, and it was exactly the same. So there is no difference between baking into hidden and visible layer, according to my experience. Also, hiding any visible Rhino or Grasshopper geometry speeds up baking. And again, I tested, and it was maybe a little bit faster when I was baking something that was hidden, but it didn't really make much of a difference. And also another thing is that you do baking only at the end of your work with Grasshopper, so you don't really bake, I don't know, 100 times per definition. So this is something that happens only once usually. And there I don't really care that much about optimization. So optimizing baking doesn't really make much sense to me. It actually makes a lot of sense if you are processing a lot of data very often, so if you do many operations. And also optimization makes sense when you are using loops. And we are coming to the loops at the end of this video. Again, if you have any questions, just post them, or any comments. If I'm wrong, just let me know. I might be wrong. I'm not always right. Very often I'm not right. But here I tried to test all the things that I'm telling you, so they should be more or less correct. So avoiding errors. This is something that in most cases when you see the fog of the war, the white overlay over a Grasshopper and it's not responding, it's usually when you make some mistake or error. And it's not really because Grasshopper would be slow, but because there is not a good way of stopping the solver except of hitting your escape key erratically. And there should be you should be very careful when you to make sure that the data that you're using is correct. And the usual reason is that it's a computational complexity, and this is something that the computer scientists and software developers and the IT guys, they are talking when they are talking to me, they're always telling me how complex a certain problem is, and I'm really fed up with this because I'm not a mathematician and I don't really care about that. But sometimes it makes sense, and let me explain on very simple. On a very simple example. So let's have a series of numbers. I will try to explain what is a computational complexity. I have a series of numbers, so let's have 100 numbers here. Sorry, it's here. So I've got 100 numbers here, and when I say this list plus number 5, let's just do it like this. Plus number 5. Alright, so this component has to run 100 times. So each number plus 5 needs to happen 100 times. If I do it differently, if I plug this here, now because Grasshopper works with the longest list data processing, it means that each number is going to be added to itself, so again it only has to run 100 times. So the result is 100 numbers. But if I graphed here, then to each number 100 numbers will be added. And you see that it takes much more time now, and the result is 10,000 numbers, just by changing the structure. But if I graphed also this one, again, it only happens 100 times. I'm not really going to explain why this is happening, but this is something, this is basic data tree processing. My point here is not that the grafting or data trees would be evil. They are not. They are actually very useful, and you should keep the data trees as long as you want, as long as you can, because when you already have your data in the data trees, you probably have a reason for that, and you probably sorted the data into the data tree before, and it can be useful, so you should keep it as long as you can. But the most important thing is that always make sure that you understand how are you actually matching two lists of data. If you are matching each number with each number, or each number with one number, you need to understand the computational complexity. So if I have 100 numbers, then the complexity, the basic complexity would be that you need to calculate as many times as you have items in the list. So this is n numbers, 100, you need to calculate 100 times. If I just change one of these graftings, you need to do it n squared, which is 10,000 times. So most of the problems with the data trees and slowing things down suddenly is because you don't have proper data matching and you increase the computational complexity. So always make sure that the data that you're passing into a component is in the correct form. There is also a comment that actually says more or less the same from Nader. He actually made I'm very happy that that you guys commented on the document. I don't know you personally, most of you, but I'm very happy that you did, and I apologize if I pronounce your name wrongly, but you've been very helpful, and this is something I'm very happy that this document is still growing, and I will keep it online, and you can add things there later on as well. Also, please try to make screenshots like this, because I will probably not have enough time to maintain the document. So to make things valuable and proven, also post a proof that what you're claiming is actually true. But let's go back to the computational complexity. Another says before, in between, and after processing. Maybe this is something I wrote, but there is the garbage in, garbage out law, which means that if the input into a component is a garbage data, then certainly the output would be garbage data as well. So always make sure what sort of data you are passing in. This is also related to the next point. When replacing a component in the middle of a definition, never plug it without checking the output. So let's okay. I already have. Let's imagine that we have this. Let's imagine this makes sense. So now I have 100 numbers, and here I want to do the same thing. So I want to, for example, graft this data and flatten this data. So here I'm okay with creating 10,000 values. And now let's imagine that I want to replace this with another component. So let me pretend not to be careful. So I will just do something like this. I will accidentally graphed it here, and then I pass it here, so I will just replace it like this. But watch out, this only has 100 outputs, and it creates 10,000 outputs out of these 100. But this already has 10,000 outputs. So if I plug this here, this actually is going to die because this has to create really a lot of data. It's how much is it? It's 100 million, or maybe, I'm not really sure. So whenever you're replacing a component in the middle of a definition, always make sure that the new component has the same amount of output as the original one, or at least it's structured in the same way. So maybe this should create more data. It's okay, but it should be structured in a more or less meaningful way, more or less similar way as the original one. So when you're replacing a component in the middle of a definition, always make sure that before you plug it to the rest of the definition, always make sure that the data is more or less the same, or the amount of data. Okay, rebuild carefully. This is obvious, but let me mention. When you are creating new geometry out of the existing geometry, this is still frozen. I still don't know what to do with it. I can try to hit escape, but I will probably have to kill my rhino, so that's not a nice thing. They are endangered. I will run another one, and let's see if this one actually reanimates. Alright, so when rebuilding, be careful. So when you're creating new geometry out of existing geometry, you have no way of expecting how big the new geometry is going to be. It might happen that Nader says, "Don't worry about my name. I became accustomed. I still would like to know how to pronounce it properly. So maybe you can write it down, and I will practice." Anyway, you already have a curve and you want to rebuild it, or you have a mesh and you want to subdivide it, or you are building marching cubes or voxels. Actually, there is a super nice marching cubes routine by David Stasiuk, so that's super useful. But you're creating new geometry out of the existing geometry, and sometimes it might happen that you set up a precision or the density of the new geometry too high and becomes incredibly slow. Sometimes it's good, sometimes you know what you are doing, but be very careful about rebuilding things. So even with voxelization, I'm not really actually sure if I have voxels here in... No, I haven't installed any voxelization plugin here. But still, when you're rebuilding, always make sure that you're rebuilding in a meaningful way, because you might end up with your definition completely stuck, and you wouldn't be able to stop the calculation. Also, make sure that you always save before you do any sort of rebuilding. Autosave would help you as well. Okay, let's go to another point, and I think this is the most important one. And it's using simple data. If you have any questions, just ask me. If you have any comments, if I'm wrong, just let me know, because I can be wrong. That happens very often. All right, using simple data. This is kind of obvious. The more complex geometry, the slower the operations. I think the most complex geometrical object in Grasshopper would be a brep, which is a polysurface boundary representative, which consists of more surfaces. So when you make any operations, just sometimes you can replace the complex geometry with some more simple geometry. So for example, you have a lot of breps in your scene. So let's imagine we have a lot of spheres. So let's generate a lot of spheres. First we need to create the centers of the spheres. So let's just do it this way. So I generated a lot of random points. Then I generated a lot of spheres. So now I have 100 spheres here. Is that right? Yeah. So It's a brep. I will just internalize it here. It's already quite slow. And I will delete this. So I already have, this is, imagine this is referenced from your Rhino, like this. And now I want to do some sort of operations with this. For example, I want to sort them, or I want to measure some distances, for example. So I can make a bounding box, not per object, but a union box, and then I misspelled something. Box properties. So this is the central point. This is the center. This is the center of the whole structure here. It's a point that is somewhere inside, and I want to measure how far the point is from each of the breps. And sometimes maybe I just want to sort them from the closest one to the most distant one. So there is a couple of things that I can do. I can pull the point. So this is the point. This is the geometry. Let's pull it. Let's pull it to all of them. And this tells me the distances. And it takes some time. The profiler doesn't really show the time, but I'm pretty sure pulling a point to a brep is a relatively slow operation. But what I can do is I can actually create bounding boxes for each of them, each of the breps. Then I can extract the central points. So I have somehow temporarily replaced the breps with the points, and then I can just measure the distance between the central point and these points. It doesn't really show, but maybe with more objects I would be sure that this operation is way faster than this. Maybe with more complex breps than just a sphere, it's going to be certainly faster to do something like this. Here I have replaced the breps with the central points, and if I want to sort them, then I can just sort these breps from the closest to the most farthermost from the central point. So number 1 will be the closest one to the central point, and number well, it's number 0, and number 99 will be the one that is the most distant. And I've done it with a temporarily replaced data, which is a much more simple data. That being said, it's actually smart to come down to even numbers, not even geometry. Points are very close to numbers because they are only three numbers, basically. But if you are able to work with numbers even, then that also would speed things up. There is a nice blog post by Edwin from the Shape Diver, who is discussing how to optimize and speed up things. I recommend it to you, and he's basically saying more or less the same. Also, it's good to know that the mesh geometry is faster than a brep or a NURBS geometry. But you also need to understand the limitations. So those are two different things. A mesh and a brep is a different sort of geometry. Brep is basically a NURBS geometry, which means that it's mathematically perfectly described, and it's got an infinite smoothness. Whereas mesh is made of triangles, and it's being subdivided and smoothed out. Sometimes it's enough for you, but Rhino is made for NURBS modeling, which is the more accurate one, but also in many cases much slower. But sometimes you don't care, you don't mind, and you don't mind actually using mesh instead of breps. This is something that when you have very complex geometry, you don't want to use breps because it's very, very slow, and you want to use mesh because it's fast and you can work with an unsubdivided mesh and then subdivide it at the end. Subdividing is actually smoothing out. But I also made a little test by just finding a section through a geometry. So there is a brep here, there is a mesh here, a list of them. They have the same shape, they're boxes. This is a brep box, this is a mesh box. So it's a cube. It doesn't have a different shape, it's the same shape. And I'm dissecting it with a plane. So there is a plane, and I'm finding a section between the plane and a lot of mesh cubes and brep cubes. Finding brep cube sections took almost 3 seconds. Finding mesh sections is 55 milliseconds. Super fast. And if this is what you are planning to do, then it's probably worth just converting from brep to mesh, even temporarily, even for the sake of finding the section and then finding the section, because it's super fast. I don't know why. I tested joining the mesh, so all the boxes I joined into one mesh with a lot of distinct boxes, and then I made the section, and it's way slower, and I don't have an explanation for this. That doesn't make really any sense to me, but oh, now I realized why it might happen. This is something that works in parallel, so because this is a list of, I don't know, 100, 1000, 1 million boxes, it could be split into multiple cores of my computer, and it could be calculated in parallel, whereas this is just one piece of data, and it's never going to be split into more, so it has to be calculated on a single core. Well, that might be the explanation, but still, you see that the difference is tremendous. Sometimes it's worth to actually convert breps to mesh, even for such a small operation as a section. And this is something that I only tested because I thought that a section might be the one operation that is basically that is faster, and it was. So maybe there are more operations, but also be careful because sometimes these operations can be also faster with the breps. But generally, in most of the cases, the mesh is going to be faster, but you're losing some precision and some nice details if you're using meshes instead of breps. My next recommendation is use numbers if you can, and also there is another recommendation from somebody. This is probably again from Myron. He says, when sorting lists, use a list of indices as a placeholder instead of any geometry. And I tried, and it actually doesn't prove to be the case. It doesn't really make any difference. Actually, it's much slower to do what he is suggesting, but maybe I misunderstood. But in general, I agree that if you can replace complex geometry with numbers, mainly if you make a series of operations that are like you make one operation, then with the result of that you make another operation, and with the result of that you make another operation, it's smart to convert data into the simplest possible data, which is always numbers, which is always indices. If you are just sorting lists somehow, then just convert them into their indices, and then make all the operations that you need with the indices, and then collect the data back from the original list using the indices. This is something that I tried here. In this case, it didn't really make any difference, or even it was worse. But in many cases, it might help. This is very specific, and I cannot come up with an example right away. But sometimes you will realize that sometimes it makes sense to just do it this way. We have a comment from Aitor on the Facebook, and he says, I would say the main difference between meshes and NURBS, a part of the discrete versus continuous natures, could be that the inner data structure they contain, which radically change the way you work with them, faces, edges, vertices versus parametrical equations. This is true, but in a way, NURBS are also described by the polygonal hull. So there is also some sort of mesh behind the NURBS, but it's being smoothened out all the time. And when you make some sort of operations, like the sections, that's why I picked the section. When you make a section, then the polygonal hull of the BREP needs to be converted into the smooth version, and that smooth version is being you're looking for a section of the smooth version, which is much more complex. So you need to smoothen out the geometry each time you are going to do something with it. Whereas with the mesh you don't have to, but sometimes the result is not so nice. Ah, Ether is agreeing with me. So yeah, and it's the everything, all the geometry is always displayed as mesh, but that's only because the graphics cards are made that way, and it might change in the future, for example, to the voxel display or processing. That's going to be slightly different then. I will take a sip of water. Okay. Another tip comes from Nader again, which is an old IT rule, but relevant. Whenever you can try to avoid mathematical divisions, you should substitute them with multiplications. For example, use multiply by 0.5 instead of division by 2. And I wasn't really sure this is actually true, but it's absolutely true, and I was really stunned. I was shocked about the difference. So I've got a series of numbers, and I divided the numbers by 3, and I multiplied the numbers by 1 over 3, which makes the absolutely same result. It's the same result, but division took 8 seconds, whereas the multiplication took only half a second. So this is 16 times faster, including the conversion of the number. You should also consider whether if you now I'm dividing by one number, and this conversion only happens once. But if I was dividing by the same amount of numbers, maybe the conversion to 1 over x would take a lot of time, and eventually it would be the same. It would take the same time. But if you can, just always use multiplication. That's a very useful thing. And I was also very surprised how long did it take to divide numbers. Another thing that I didn't know, again, it came from Nader. Extensive floating points steals a lot of your machine's raw power to create useless junk. Solution: rounding the values before processing. Now, this requires a bit more explanation. In most of the programming languages, you have different number types, and some of them are whole numbers called integers. Yeah, another is now commenting on Facebook. The algorithm for division on the CPU is harder and longer than that of multiplication. Yeah, but that's true. But I believe that internally on the CPU, it's actually doing exactly the same thing as I'm doing here. So it shouldn't be any difference, but it obviously is. Now this floating points. So multiple number types. One would be the whole number, which is called an integer. Another one would be a floating point number, which is like 1.5, 1.68, and so on. Even 1.0 is a floating point number. And those operations, now operations with those numbers, are much slower on the CPU than operations with the integer numbers. In Grasshopper, you basically just work with numbers, and it doesn't really show much of a difference, and by default all the numbers are floating point numbers. So if I create a series of numbers like this, if you use the panel, you see that, oh no, it doesn't really here. Maybe this might have changed. Oh, but well, let's see. I'm just going to I was using a much slower computer than the one that I'm using now, so let's make 1 million numbers. And I think by default here they are floating point numbers. So this plus this takes some time. So it's 1 point, no, it's going to be more. But I know they are whole numbers in their nature. So I don't really need to treat them as floating point numbers. Yeah, it takes some time. Maybe I shouldn't have picked 1 million. At this point, I'm really curious if my previous definition has woken up. It took 4.6 minutes. That's the error that I made intentionally. And the result is maybe around 100 millions. Yeah, it's 100 millions values. Let's come back to this one. So it took 26.5 seconds to add number 3 to 1 million floating point numbers. Now let's convert these numbers, these floating point numbers, into integers. And I'm going to, and in Grasshopper you can do it easily by passing it into an integer a parameter, which is also typecasting. So we've got two new comments. I should try 1.0 into s or maybe into n to come out to turn them into floating point numbers. And also Giancarlo says that they were floating point numbers in Rhino 5, and I remember they were. Anyway, so I converted this into integers now. Maybe they are integers. Oh, I made a copy. So again, I made a mistake. I should have been a little bit more careful. Now this became too slow, but let's come back. Okay. So I just want to plug this one here. I want to make sure this is an integer, and let's see how does it work here. So I first plugged this one here so that I don't have to wait at the beginning, and now I will wait. And if these were already, no, you see they were still floating point numbers. I think it's the panel that shows them as whole numbers, integers, but they are still floating point numbers. And you see that adding the whole numbers with the same results takes 2.3 seconds. The same numbers treated as floating point numbers, it took 26.5 seconds. So my recommendation is, when you know that you're working with whole numbers, use this component integer, which actually makes the data casting, typecasting from the floating point to integer as often as you can. When you're working with indices, for example, use it, because then you're working with the whole numbers, which is much faster. Also, this makes sense only with large numbers, so we've got 1 million numbers, but if I had 100 numbers here, it wouldn't really be much of a difference. It doesn't even show the bubbles anymore. So again, don't over-optimize things. If it doesn't really make much sense, don't do any optimization that doesn't really make sense. Here, I wouldn't really care. With 1000, it doesn't really matter. With 10,000, yeah, it already might. I might already consider doing this. Mainly if this was in a loop, then it would make sense. All right, let's go to the next one. Yeah, I've already done this in this example. Use placeholders, points, and numbers for complex data like groups and breps. This is something that we have done. If you can, use a more simple data type. Do whatever you need to do, and then somehow reflect the result into your original data. So if it's sorting or something like that. Another is commenting. I should add something. When you have to work with floating point numbers, try to reduce it to the minimum accepted limit of precision. I know what you mean, but I don't know how to do it. How can I change the precision of a floating point number? Let's see. Maybe it's somewhere in the preferences. Solver. No, I don't really think so. Maybe he will comment again, but I've never done that. So as far as I understand, this is he means that you can say you only care about the first two digits behind the floating point. But I don't know how to do it here, and I'm not really sure if it actually makes any difference, because in other programming languages it wouldn't really work at all. So let's see. I will pass the definition. So please then post it into the comments so that everybody can see, and it will remain in this feed. I will just go on. Okay. Another point in the document is using code components, but let's keep this as the last thing because this is more complex. I will just skip it and I will come back to it. Filtering relevant data. This is something that is this is not a simple click solution or simple thing click help, but this is a practice that you should actually do. Um, if you have if you know that you're going to need only certain part of the list that you have in the next step, then just filter it or just remove the unnecessary data as soon as you can, so that you don't really process all the unnecessary data when you know that you're going to remove it. Remove it as soon as you can. Sometimes you can't, but usually you can pretty soon. Okay, so let me give you an example. My first point is if choosing between two possible operations, bifurcate the input data before processing. So what I mean is this. Let's have a list of random numbers, which is vector this here, populate, and these are some numbers. So some points here. So I've got a lot of random points here, and they are between, what is the size of this box? Let's see from front. So they are vertically between 0 and 2 points in height. So some of the points are between 0 and 1, and some of the points are between 1 and 2. So now I can, let's say that I want to make spheres around the points on the top, and I want to make boxes around the points on the bottom. So let's make a box, center box. So I will create boxes around all the points here. Let's make it much smaller. So that's what is the size now? The size now is 1, so let's make it 0.2 maybe. Maybe that works. Alright, so let's just make it visible better. Sometimes I find what I'm going to do right now, I find it nicer as a definition, but it's very unoptimized. So first I created, out of those points, I created boxes around all the points. Now let's create spheres around all the points. And it's quite slow. Alright, it doesn't really show the profiler anymore. Again, I don't know why. Let's see, profiler, display, profiler. I believe it's because of the broadcast. But anyway, so now around each point there is a box and a sphere, and I want to only keep spheres on top and boxes on the bottom. So let's see if the point is above the z value, if it's above 1. So is the z value larger than 1? And this gives me a Boolean pattern, true, false, and so on. So I want to filter, is it filter? Stream filter. I'm not really sure, but no, it's not stream filter. It's the other one. I always mix these up. It's either weave or sift pattern. I think it's sift. No, is it weave? No, it's pick and choose. Okay, I'm always puzzled with these. So if it's larger than 1, then I want it to be a sphere. If it's smaller than 1, I want it to be a box. So I will hide all of these, and I will keep spheres on top, boxes on the bottom. This is kind of wrong in a way, because now I created 100 boxes, 100 spheres, then I just sorted them out, and now I have around 50 boxes and 50 spheres around. But I had to create 100 of each first, which is very unoptimal. So let's do it in a nicer way, or in a faster way. So first I will just, because I know that I'm bifurcating, I'm just splitting it into half. I need to have this here and this here anyway, so I'm basically making two things. Like, I need to have two parts of the Grasshopper definition. So let's just dispatch the original list of points according to this, and let's just create spheres on the top and boxes on the bottom, and I don't need the pick and choose. And I only created around 50 boxes and around 50 spheres. This is 52 spheres and 48 boxes. If I want to have them in the original order, I will just use the weave, which is probably like this. So they should be here. Yeah. This should be faster than this. Maybe in this case it wasn't, but in general, as a practice, this should be faster because I bifurcated the input data first. I split the data into the parts that need to be taken separately first, and then I only made the slow operation, which is the data creation, only on those data that needs to be, that belongs to that part of the operation. So instead of creating 200 elements and then sorting them, I just created 50 and 50 roughly and then sorted them. All right, let's go to the next step. Filter only relevant data for slow operations like intersections. Use the shortest meaningful data set. I'm not really going to show you this because this is kind of difficult, but what I want to say is that intersections in general are super slow, just like the Boolean operations, like somebody suggested at the beginning. And if you want to intersect, if you're calculating the intersection of two geometries or two elements, or many elements and many elements, just try to reduce the set to only those that actually can intersect. So if some of the objects is too far from your object, then it doesn't really make sense to look for an intersection. And there are many ways how to do this. If you know a rule, because you created the data usually, if you know that there is a rule that disqualifies certain geometries from the intersections, you know that these geometries never become part of the intersection, just don't put them there. Filter them out, just get rid of them as soon as you can, and then only calculate the intersections or any other slow operation only on those elements that are relevant. I tried to explain this a long time ago in my flocking tutorial, which is here, but I will show you. Somehow it's an iterative and there is flocking 1, flocking 2. This is in the Boyd library that I made a long time ago, and there is this component align, which means that you have a lot of points and they're moving along certain vectors. And sometimes, this align actually changes the motion vector of each of the points to an average of the group. So eventually, after a long time, all the points will travel in the same direction. They will have the same motion vector over time. But sometimes this doesn't make sense if if you imagine that these points are, for example, birds or fish, they can only align to those other birds or fish that are visible. So that's why I made this component here that is filtering out the invisible elements. So now, if I use this first and connect it properly like this, it's actually, it works something like this. Now this has to be grafted and so on, but watch the tutorial to actually see it. This basically, originally, if I if I do this, then each point is going to be aligned to all of the other points. But here it's only aligned to those that are visible, so a much smaller group of points. So if this operation is slow, then it's going to be much faster this way rather than this way. Because now the comparison set is much smaller, the data set is much smaller that I operate on. Also, the same is with proximity 3D, for example. This finds the closest neighbors, but it only you can define the minimum and the maximum radius to search for. So even if you want to look for 5 neighbors, you know that they are. Let's try it. We already have some random points here. So this actually creates some sort of connection between the neighbors. And I know that it's meaningful to look for a neighbor in a distance of maybe 1 unit. So even if I want to look for 5 neighbors, now it takes 20 milliseconds. I don't know if I really speed it up, but the maximum search distance should be 1. Like this, because otherwise it doesn't really make sense. Well, eventually they are farther from each other, so it should be maybe 2. I don't know, you will find it somehow. So it seems like the connections are there, and it seems to be faster this way. Let's just try. I'm going to make 2 of these, and let's create 500 random points. So this is how many? Yeah, even now it seems like this one is slower, but I don't know. No, it proves to be right. Even maybe with 5,000 it would show even more. So yeah, it doesn't really make much of a difference here, it seems. But still a little. So now here I reduced the search distance to only those that are closer than a certain distance, which is 2.0, and therefore I think that I helped this component to speed things up. But this is too straightforward. Usually when you create your round geometry, you know how did you create it, and you know what is the condition. So try to condition out those that don't make any difference, and then you reduce the number of data that you're operating on. So that was the whole point of this this point here. Let's skip a little bit. Again, I will come to this later on, and let's go to the Grasshopper Architect live connection. This is again a comment from Nader. And I don't know, I've never used Archicad and Grasshopper live connection, but it seems like when he says using Grasshopper Architect live connection, Archicad live connection could put a strain on your computer resources if the data that being transferred back and forth between Archicad and Grasshopper is huge. So it's better to deactivate the option of sending changes from Archicad to Grasshopper until it's needed. And this is again very similar to locking the solution, but also I think it's much more similar to not reading from a file only when you actually know that it's needed. So again, the same thing. If there is slowly changing data, outer data, then just update them manually rather than automatically. Sorry. Again, I think the same can be applied to the geometry pipeline. I don't know if you use it. I started using it a lot, and also I'm using it from some third-party plugins. Like I think Human is actually good for referencing geometry pipeline. That's a built-in component where you can actually reference geometry just by defining the layer name. The problem is that whenever you change something in your Rhino, it references the new data again, and sometimes it can slow down everything. Even Rhino, even Grasshopper, everything is going to be slowed down. So sometimes this is not a good idea to use this component and rather just reference things manually, because you know that you have changed something and you have time to actually get ready to reference the new data. And before you do it, you just save your Grasshopper file, you save your Rhino file, then you reference the new data. If it crashes, you don't care because you have saved all the changes. When using geometry pipeline, if you change something, you can just crash your Rhino without even knowing how. This GH I will come back to it later on. Now there is something I would like to. Now let's go to the utilizing paths, and I think this deserves a separate tutorial, and I'm putting it together. But I will show you now what do I mean. Let's still have those points that are between vertically between 1 and 0 and 2. What I mean by utilizing paths. Sometimes when you are sorting data or geometry, it seems like there is an easy way of sorting data by reading certain value and converting it directly to a path, to a data path. And it's incredibly fast because you're working on some sort of a meta level rather than on a level of geometry, and it can help you a lot to speed things up. And I've been using this a lot recently. The good thing is that the data path, the data trees in Grasshopper, unlike indices, they can be anything. So you can have a if you look at or we don't have to look at the tree statistics, but we can even look here. You see that the path here is called 0, 0. But it could be even 100 without having all the numbers before. It can be any number basically, or any chain of numbers, which is good because you can have a data tree that has a branch number 3, branch number 100, and branch number 300, and nothing else. This is quite useful. So how can we utilize it to sorting data? This is good for example, when you need to sort geometry into the floors. So let's have the points. We can have the points even. Let's actually work with more complex geometry. Let's work with this. I'm just going to switch this on. Let's imagine that we have some geometry coming from Rhino. And that probably came from SketchUp because everybody is using SketchUp, which is incredibly annoying, but that's the life. So we have some geometry. This is the geometry. And now I want to sort it into those that are in the left half and those that are in the right half, for example. So I will just make bounding boxes. Again, I'm simplifying my geometry. So box properties, I misclicked. I converted the geometry into points, which is a more simple data structure. So now instead of working with geometry, I'm working with points. Now let's deconstruct the points. And now each point has the x values, the y values, and the z values. So now let's start with a simple thing. Let's sort all the geometry according to the z value. So I can take the z numbers, the z values, and round them naturally. Actually, I need to floor them. So some of these points, when I floor the number, the z value, it's either 0 or 1, because whatever number it is, it's being floored to the closest whole number. So now each of these, like I have a list of 100 values, 0 and 1. Now I can sort the points or the geometry into branches, either branch number 0 or branch number 1. I do it like this. I graphed first so that each element has a separate branch now. I can see the tree statistics like this. Now each point already has its own branch. I don't care. I want to replace the branch with my new branch. So I say replace path. I'm replacing the path of this data from what it is now to what I want it to be. I end up with this sort of a data structure. I've got two branches. One is 0, one is 1. Branch number 0 contains everything that is between 0 and 1, and it contains 48 values. And the branch 1 contains 52 values that are between 0 and 1 and 2. So this is incredibly useful, and we can make it even more useful. So let's say this is z, but I want to do the same for x and y as well. So I want to actually create a separate branch for each cube or space chunk that is delimited by the whole number coordinate. So I want to put all the geometries that are between 0 and 1, 0 and 1, and 0 and 1 in the third dimension into one branch, and then each cube should be in one branch. For that, I need to create path, construct path, and this works like this. I need to input like this. No, let's do it like this. 1, 2, and 3. I need to graph them first. 1, 2, and 3. So now I ended up with this data structure. So this would be the first level of the data of the path, second, third. I will create the paths. So now these are the new paths. I need to flatten them. And now I'm replacing whatever the path was before with a new path. And now I ended up having data structure that actually is like each cube in the space contains is one branch, and it only contains the values that the geometry that is inside of that cube. So for example, here are two geometries, and maybe some of them are empty because they don't even exist. Those that are empty, they don't exist. And this is incredibly useful and super fast. It's basically no time. This is the slowest operation to make bounding boxes. And you can sort geometry out. You can sort geometry into levels, into floors, and you can even make some better operations. So, for example, I want to make a branch for two of these units in the x direction. So I will just divide it by 2. And as we said, multiply by 0.5. 0.5, round, and then it creates less branches. Now each of the branch is delimited by 2 units in x direction, 1 unit in one y direction, and 1 unit in z direction. I can do the same for y, and it would be like this, and I have even less branches. So this is incredibly useful, and you can convert numbers that you read from your geometry directly into branches, and it's sorting geometry really fast. We've been using it mainly for some sort of map organization or floors. You can determine whether a building is inside of some quarters in some district because it belongs to certain index of area or something. As I said, I believe this deserves its own tutorial, so I think I will make a dedicated tutorial to this topic. This is something like how to use data trees extensively. I'm not sure if this is clear, if this is understandable, but I've been using this a lot recently. So that's utilizing paths, and I will make a better tutorial for that. Now let's talk about anemone. Actually, how many of you are using anemone, whatever? It's this plugin by Mateusz Wierzycki. I use it a lot for flocking simulations, but I basically use it for everything. When the functional way or higher order functions like map, um, this is well, if that's not enough for me, then I always use the loops. How many of you do actually use anemone? Do you? Okay, now there is not. It's incredibly useful, and it's if you don't use it, then maybe this part is not really relevant. Um, but let me just show you what does it do. Sometimes this is incredibly useful. So you basically have these two components, which is called loop start and loop end. Maybe you know hoop snake. Hoop snake is very similar, but this is, I think, a bit more advanced. Um, well, Python for loops, that's a whole different story. It's of course you can use Python for loops, but then you're looping only inside of the Python component, and this can help you loop parts of the Grasshopper definition, which is a whole different story. It's much more useful. It's super slow, but it's very, very useful. Also, you can do recursion here as well, if you do it in a smart way. If you are experienced in functional programming languages like Haskell, for example, or well, even JavaScript has some higher order functions, then this loop is basically a reduce or a fold. But anyway, let me explain how does it work really quick. You have loop start, loop end, whatever is in between is being looped as many times as you say here. So let's say 100 times. So you have data that enters the loop here. So this is the data. Originally it's number 1. Then it's being flushed out here, and it's still number 1, right? Then I can say this data plus 1. So it's number 2 now. I return it here. Then it comes back, and now D0 is whatever came here, and this happens 100 times, and eventually you get the result here. The good part is that you can do whatever you want inside, and that what you do could be some sort of animation. You can save the screenshots. You can do all sorts of operations there. You can make additive geometry generation, any sort of iterative design approaches. So this is incredibly useful. So I'm just looking at the Facebook feed. Yeah, GH Python lib. Yeah, I will come back to the Python part. Honestly, I never use Python or any coding language in Grasshopper. We'll come to that, but I think you're completely losing all the benefits of using Grasshopper when you use any sort of programming language other than Grasshopper. That's the whole point, is that it's visual, and then that you have an instant feedback. But we are going to we're come back to this, and I think it's very different. And also this is more accessible to the newcomers than just writing a Python code. Okay, so so this is how you actually make the loops, and I have a couple of recommendations. So let's start with fast loop. Well, starting from number anemone number 2 or something, there is something called fast loop, which is basically the same, except that it you cannot it here when the loop happens, you see that it's happening, and it's kind of slow. It doesn't really get much slower when you get more components here. It's like, yeah, if they are slow, then it's going to be slower, but it's not because this is slow. Up to some points, it's going to have the same speed. If I do the same here, the result here at the end is going to be the same, but it's going to be calculated much faster, no matter what you plug in here. So let's do it like this, and it's done. Well, no, it's done now, and this is like, you see the difference in the speed. So this is super fast. The problem is that here with the original anemone, you can have either constant output, which means this is constantly outputting some data, or you can output after the last. Now it has no output, and when it's done, it gives you the last number or the last result. This is always running as the output after the last. This is, you cannot really output the data as you go. Another thing is that you cannot really, when this is running, you can double click here and you pause it, and we are at number 15, and that's kind of you can check what is happening. You cannot check what is happening here. You cannot stop it just prematurely and just see what the result is and then resume it. You don't see the animation. If I do something like let's see, I will just construct a point. It will be like this. So let's see, just this, and there should be a point somewhere here, right? If I do this, I see that the point is moving, and eventually it stops somewhere. If I do the same here, let me hide this like this. Okay. So if I restart it, you see that the point is moving. If I do the same here, it's not really moving. Eventually, if I care about the last result, it's the same. It doesn't make any difference. Here you can record data. So I can even add more values here, and I can record the data here. So eventually I will end up having all the positions of alright, so I'll get all the positions of the point here, but the same applies here. If I record the data, then it's fine. It's going to be the same. So record data, I will disable this, and you will see that it basically super fast. It's super fast. It generates all the points all at once. This is super fast, but you cannot really enter what is inside. You don't see how it's animating and so on. Another thing is that if I keep something just inside of this loop here, and if I check here, now I know that the loop is over, and this is going to contain the last value that is being passed here. This, not really. So when I even check what is the number here, it's 0. That's number of repetitions. If I check the number here, it's 1. Even though here it's going to be 100, and here it's going to be 101. So what is inside of the fast loop is not reliable. That's one thing. And also you have no way of seeing what is inside. So I'm actually almost never using fast loop, but sometimes for mathematical operations it's nice, it's good. I'm checking the Facebook now again. Yeah. So people are fighting about using Python or not. I personally, I don't use it. I understand why people do, though. Okay, so back to the anemone. So use fast loop carefully, because sometimes you cannot, well, you never can rely on the values that are inside. And sometimes, because it happens at once, if you make a lot of repetitions, like give me an example. Let me give you an example. So if I say repeat this 100,000 times, this is just going to slowly run, and I can pause it anytime and so on. It's okay. But this runs at once, and maybe it will freeze my computer. I don't know. Let's see. Yeah, you see, nothing is happening. It's kind of frozen. So be careful about the fast loop, because even though it's called fast, it can actually be eventually quite slow. And it generates a lot of data. And with the slow loop, you can actually see that it's already generating a lot of data. Okay, maybe, yeah, 26 seconds. Yeah, that's crazy. Let's just not do it. Let's just not. All right. You can also stop a condition, stop a loop when a certain condition is met. So there is an input called exit, and when you set this to true, then then this stops. So give me I will not you. I will give you an example. So now this generates 100 points like this. I will just disable this one. So this generates 100 points, just like it did before. But I only need the 50 of those. And sometimes I'm not really sure how many I actually need. So let's say I've got number 50 here, and I'm asking, is this larger? This number is larger than 50. If it's true, then stop. So let's see. I'm starting now, and now it should stop at 50. So use this, because then you can repeat really many times. It never happens because it stops at 50. This is good for something that for loops that are not defined at the beginning. You don't know how long the loop should actually last. So it's good to stop it on time. The same applies here. It speeds things up. Another thing is only loop what needs to be looped. This means that you can maybe just generate data, or, well, I don't know, if I don't know. Let's see. Let's say I need to. If I'm going to generate a series, for example, here, starting from 0 to, well, that doesn't really make much sense. Generally, what I want to say, whatever is here inside is going to be repeated as many times as the loop iterates. So only keep the necessary operations here. So for example, generating the point, which is not a slow operation, but imagine it's a slow operation. Generating a point doesn't really make much sense here. Or let me do another thing. Sphere. I can create the sphere here and just store it, record it here if I want that many spheres. But this is going to be really slow. So because I'm repeating the sphere creation inside. But I already have the points here, so instead of repeating or creating the sphere inside of the loop, I can do it afterwards, or even before. That's even better, if doing things before rather than after. So if you are able to pre-calculate certain data, then do it, and then your loop is going to be much faster eventually. And even the sphere creation is super fast. So now it executed much faster. Only loop what you necessarily need to loop. This here, I can do even more things. I can create, I don't have to even loop the point creation here. It's enough to create points from numbers that I created and then the spheres. But it even more makes sense before the loop. Another thing that might not speed things up, but I think is a good practice, mainly for the fast loop, that you should encapsulate the loop data and operations. This doesn't matter that I placed this here because that's basically inside. But with my other definitions that I was showing you, I made the mistake by interconnecting things that are coming from outside into components that are basically logically inside of the loop. So it's not a problem to plug this here. I don't know what it is, but you can do it. It's fine. It doesn't crash. But I think it's not a good practice. A good practice is to keep encapsulated whatever is inside. And I would go that far that even if you have something that comes from here, I don't know what the data is. It doesn't really matter what the data is. I would recommend you to create a new input pin here and here. Input the data here. Then use it from here, whatever it is, and then pass it back without any change. This way, this is still encapsulated, and what comes in also comes out. So the good thing is that you can replace this easily for the fast loop. If this works well, you can replace it with a fast loop. Also, you can cut your definition here and here. You can split it into more definitions. And also, for the fast loop, I think there is a problem when you pass something from outside. It might not be calculate it correctly. I'm not really sure. We should ask Mateusz. I'm not really sure, but I think it's a good practice to encapsulate everything that is inside. So whatever is happening inside is only happening inside. That brings me to another thing. Never link components from inside one loop into components in another loop. So potentially you can have another loop that is here. If you've been using anemone like this, then you know that just going to do something like that. This doesn't really make sense, but if you've been using anemone like this before, you know that this is going to be triggered only when valid data comes here, and it's only going to loop when valid data comes here to the end. So I will zoom in a bit. So whenever, if this wasn't releasing data after completion, it would trigger this second loop each time this one iterates. But they don't wait for each other. Therefore, this one iterates 1. It flushes the data here. This gets triggered and starts calculating, and if this one is slow, it might not even finish, and this one already releases another value and restarts this one. So this is going to be restarted all the time, and this slows down your computer significantly. Another very bad practice is making a connection like this. This means this is being changed very often, this is being triggered somehow, and this is being changed again. Some valid data is coming here, and this is re-triggering the whole second loop. If you do this, it's going to slow down things like hell. And I made a mistake like this for my current work when I was making the animation that I posted on Facebook. It was so big that I couldn't really find a solution for that, but I had 4 or 5 loops behind each other like this, and they were triggering each other and also saving some files on the disk. So it was incredibly slow, and I was so angry at myself that I wasn't careful enough by encapsulating whatever is inside and never reconnecting like this. Well, I didn't do this, but I somehow was triggering the parts of the loop that was behind my current loop. Alright, this is, I think, it about anemone. Yeah, that's it. And let's come to something that most of you have been already suggesting, and it's using code components if you can. I never do, but it doesn't mean that you shouldn't. I never do because I really like the way Grasshopper works, and if I want to write a code, I do it somewhere else. We do a lot of programming at my office, so at our office actually. We create a lot of software, but we use dedicated programming languages for that, and we don't really make scripts. But you can. It's perfectly fine. And I was kind of nicely surprised how much it can speed things up if you do it properly. This is a suggestion from first suggestion from Patrick, and he says for mathematical operations with long lists, it should be lists, use code. So I made a little test, and if in this cluster I'm having addition, subtraction. Can you actually see it? I'm just going to zoom in a little bit more. No, it doesn't allow me to zoom in. Okay, you need to trust me. So the operation I make with 100,000 values is x plus y minus z divided by u. And first I used Grasshopper native components, and it was yeah. Anyway, so this took 27 seconds. I really believe that using a formula would be much faster than chaining 3 operations, but it was actually slower, and I was very disappointed. So this is not a way. And I actually never use it, but I believe that this would be the fast way. then I used C# and Python in a wrong way. And probably those of you that use the code that you already know, but for the newcomers, this is kind of an important information. So if you use the code component with item access, so you can define for each input. I will do it in Grasshopper. So if you have a C# component, for example, you have two inputs, and you can divide them. You can define them. You can either type hint them. Well, that's very important. You can say it's an integer or a double or something. So let's say it's an integer. And you can also say if you're going to access the values that are coming in as an item, as a list, or as a data tree. So what happens is that if you access things as data as an item, it's the same like the formula here, which means that if you pass this value here, this formula is going to be executed as many times as you have the values here. So basically, the whole component is going to be processed as many times as the values coming in. So if I have 100,000 values, this component is going to be executed 100,000 times. Now, that's not technically true. It's the function that is inside that is going to be executed 100,000 times. But if you make a list access, then this is going to be, if a list comes in, this is only going to be executed once, and you need to process the list inside. So you're basically reading item by item in the list and doing something with it. And that's what I did here in the second example. And here you see it doesn't take 27 seconds or even 32 seconds, but it only takes 2.3 seconds to process the same data. And that's more than 10 times faster than using Grasshopper native components. So yes, it makes a lot of sense to use code if you do mathematics or even if you do other things. But as you see, maybe I'm not so skilled in C#, but the code is much longer and it requires a lot of thinking here. I tried the same with Python. The item access is even slower. It's the slowest of them all. So it's 41.8 seconds. But if I do list access, it's only 2.7 seconds. And you can use this nice functional programming approach here. You can write it down as a map function. If you are familiar with this, then congratulations. This is a super nice way of doing things here. So yeah, using code speeds things up significantly if you use it correctly. Another tip comes from Nader again. If working with numbers or simple elements and operating with many conditions, no, this is mine actually, try using code. This is something that doesn't come automatically, but using code in if you have patterns like true for false patterns that we've been using in those previous here, like for weaving and stuff, you still need to create a lot of data. You need to create a pattern that is quite long. So this is a condition. You're asking whether something is larger or not. I believe that it's much faster to do it inside of a code because you don't create that much overhead data. You can ask, and if something is true, then do something. Instead, here you create data structure that is used for dispatching and weaving. Still, I don't do it personally because I like to see what is happening here, but this would probably speed things up even more. What Nader says, that the Grasshopper components have too much code to be processed by the PC, just see the XML. Luckily, scripting can combine some of these steps into one, or even for IT languages beginners. I think this is a bit more complex than for beginners, and also I have to say that it's not because the XML is so long. The XML is basically describing these components, and then it's being translated into API, the Grasshopper API. So the reason why this is slower is not really because it's XML, but because of what I said, immutability and a need to calculate the actual values for each step. but you're right that you can combine more steps into one, and even conditions and even other more complex things into one if you're using scripting or just any programming languages coding. But still, you're losing a lot of nice features that come with Grasshopper. If you are more, if you're comfortable with that, then it's fine and it's going to run for you much faster. Um, I thought originally that a use of equation instead of multiple math components would be faster. That's this. It has proven to be wrong. This is slower. Then this is not a good suggestion. Another thing comes, another command comes from Nader again. When writing code in any programming language, add meaningful comments. Um, this is a good recommendation, but also, um, there is a funny meme. Because when you write a code, just like I did here, without a good description, I might not remember 2 days from now what does this mean. So maybe just add some comments. Um, if you are familiar with if you are working in a familiar programming language and if you are just using basic things, you can take another approach. You can use something that is called a verbose variable and function names, which means that instead of using variable names x, y, and z, I would just call them with a full name, like all the numbers from the series instead of x. And that when you know how to read the code, that basically tells you everything that you need to know. So sometimes you don't need to add the comments, but I think it's a good practice to combine. If there is some untypical or unusual part of the code, then use comments. Otherwise, use very verbose names, like use long names describing everything that you do. Um, Also in code, but also do it with your Grasshopper definition. And there's a recommendation that I have. This is not speeding things up, but that's a good practice. Instead of you can in Grasshopper you can rename this to hello, for example, and you can rename this to world, for example. If you do this, and even if it's meaningful, this actually kills your this kills the definition because you have no idea what hello is doing and what world is containing. Instead, I would just go back like this, and then I would create a group, and I would describe everything here in the group. Or you can use any other options, like you can use a panel and put it into the same group, add to group, like this. Or you can just use this. Whatever works for you. Just my recommendation is never change the way the components look originally, because then they become cryptic. All right. New comments. Yeah, verbose variables might not help if you have an extensive script. Oh, that's true. Yeah, sometimes, yeah. Besides, comments will help you to pinpoint what have gone wrong in the script. Yeah, that's all true. I can just show you. We have been. This is a completely different project, and yeah, I can show you. There is a lot of programming that we have done, and sometimes you see that the green parts are the comments, and I'm not really sure if this is the latest version, but maybe it is. Here in the code, I tried to use names that explain everything. So let's see. This is called Pixel Blend Alpha Over, and this, you see, everything has a really long name that is describing everything. Oh, you don't see it. Okay, let me just zoom it in. Is it already better? I hope so. So you see that the names are super long. Yep. I'm I made sure that everything is well named, and you can actually read it as a novel, because you know what is happening there if you understand, if you can read the code. But sometimes I use comments like this one if something is not really clear. So, for example, I found this is some mathematical operation, and I assumed it. I didn't know how does it work, but I found a Wikipedia article, and I assumed that it works this way. So I somehow translated it into our code. And also sometimes when you don't know what the code is actually doing, then I describe what the code is doing here, and then where can you read more. So it tells you stack the current layer onto the layer below. If you know what the program is about, then you would know. The bottom layer is visible only where the top layer is semi-transparent. This is something that is not completely clear from here. This describes what is happening in the code, but the rest of the code is described using very long names of things. It's a combination of one and another. Okay, this is my comment, and it seems like many of you will disagree with me, and you might be right. That's why this is in italic, and this might be completely wrong. But I claim using code makes little sense when calling Grasshopper or Rhino API, which is something that one of you was suggesting also in the discussion on Facebook, and also it appeared here, GH this actually is a good point, but it seems like it's possible to access the Grasshopper components and Rhino commands from either Python or C#. For me, this doesn't really make much sense because it doesn't speed things up per se. It only speeds things up in special cases if you do smart things in the code. If you don't, then this is not a rule of thumb. It's not always the case that this is faster. It just makes things. It always makes things much more complicated. If you are able to write the code in Python, then do it in pure Python. Don't use Grasshopper. That's what I do. I always start a new project that looks something like this, and that's a complete geometrical library, because eventually it's going to be faster to run something outside of Grasshopper. But again, I understand why you're saying that. I personally don't use code in Grasshopper, and I wouldn't probably use code in Grasshopper when calling Grasshopper components, except a suggestion that is here that is completely right, but I don't have it proven. Again, it's from Nader. He says, your computer is a multiprocessor, multi-threaded CPU, and with Rhino 6, multi-threading your script in GH have become easier. You only have to add few extra lines of code. So take the advantage, and there are some links here. I will just incorporate it here. I don't know, I haven't tested, but it makes sense. As I told you, the multi-core or multi-threaded processing works like this. You have a long list of data. You split it. If your CPU has 4 cores, then you split the list into 4 equal chunks and send the same processing, the same instruction on those 4 chunks to the 4 cores of your CPU. So they are being processed 4 times faster, except that you need to split them first and then connect them again. If it's possible to call Grasshopper components like this, then it could be very useful for large data sets. So if the breaking and connecting makes sense, if it's worth the effort, then this could be probably a good way of speeding things up, because you can process your data on multiple CPU cores, even if the component itself is single-threaded. So this is a good practice, but I don't know really how easy it is to implement. When I was testing some multi-core processing in other programming languages, it was usually some library that spawned some process, and it seems the same here. So you basically just manually create a process that you send to the thread. It processes itself and it comes back when it's ready. You can read the articles that were posted here, and I think that will explain things. Um, let me see what is. I think there is just one last comment here. Yeah, again from Nader, and here I disagree. He says if you're starting to learn Python, learn the basics of lazy functions and iterations. You will thank me later. Just see this video. The video is good. The reason why I disagree, I will try to explain, and this is going to be a little bit more technical. There is something called lazy functions in some of the programming languages. By lazy, it means that if you are processing, or lazy lists, imagine lazy lists. When you have a list of data in Grasshopper, it's basically an existing list, like a list of numbers. A lazy list is a list that could contain the numbers or will contain the numbers if you request them. So imagine that you have numbers from 0 to 100. And if it's an actual list, each of these numbers exists somewhere in the memory. If it's a lazy list, there is some sort of a function or a mathematical operation. Then when requested, it tells you what value is on that item index. So it doesn't really exist anywhere in the memory. It's being calculated. And chaining these lazy lists one after another is quite smart, because you can chain them without doing any calculation. You only do the calculation when you actually need the data. So when you request the data, it's going to be calculated. So in Grasshopper, when you have component, like one after another, like one component, another, here it creates the data, here it creates the data, here it creates, there is a lot of data. When you have lazy lists, you don't create the data here, you just almost create it. You just have the function that creates the data. You come here, you have a function that takes that data that doesn't exist yet but will sometime, and will do some processing with it, and then you do the same, and so on. And at the end, you request the actual data, so it's actually executing the whole chain from the end to the beginning. As such, this is not faster. You need to do the same processing. It's about the coding style, and I have to admit that it's a very beautiful coding style. Lazy coding, some programming languages, as far as I know, Haskell, for example, is inherently lazy. Everything is lazy in Haskell. Everything is only being calculated when you actually need it. There are two reasons to do lazy processing, though, and one reason is if you can have infinite lists, like you can have all the positive numbers, and it's impossible with the actual lists. You can have an infinite list because you would need an infinite memory. You can have infinite lazy list because you only request those items that you need, and eventually you are going to reduce it to something much smaller. So you're just going to use a couple of those values from that lazy list. That's one reason. Another reason why to use lazy lists is when you want to save, you're saving memory, but also when you are this is also saving memory is also good for example, reading files. That's a good example. When you're reading a file line by line, you don't want to read it at once, you just want to read it line by line, and you can do it very nicely using lazy lists. Another good reason why to use lazy lists is when you eventually at the end want to reduce the list and only use a couple of values from that list. And that's exactly my first example with those, using, where was it? It probably was even here. No, it was here. Here when I was dispatching at the beginning or dispatching at the end. If this was lazy, then dispatching at the end would be fine, because those values that are not here in the final dispatch, those are not going to be ever calculated if this was lazy. So if you are smart, then using lazy lists inside, or lazy processing inside of your Python script makes sense, but it has to be quite a long script. But if it does only one thing, and it's returning the data immediately, then using lazy processing makes zero sense. I also made tests here, and you see that this is lazy processing, this is imperative processing, and this is functional processing. It does the same thing, it's just different coding style. I personally prefer this one. This is the easiest one. This comes from the C language or C++. That's the most basic one, and this is lazy processing, and it's actually beautiful. I think it's almost as nice as this, and this might be lazy as well. I'm not really sure. But you see that when you see the performance, it's very little difference. It doesn't really make much sense. Also, I tried with much more numbers, and the results are even worse. Like it's more or less the same. The reason is that here it's being actualized. It's being calculated anyway. So the lazy processing has zero benefit when you eventually want to calculate the data anyway. So why do you want to do it lazily? Only if you either reduce it at the end, or this is a longer Python script, and at the end you don't want to use all the values, or if you are reading, if you would spend a lot of memory, this saves a lot of memory. But still, even with these numbers, the memory it used, it was nothing really. So it didn't really consume much memory anyway. So that much about lazy processing. There is a lot of comments on Facebook. Maybe maybe somebody doesn't like what I'm saying. So let me read the comments. And actually, this is all. I don't have much more recommendations for you, but let me read the comments first. Maybe there is something. Scripting in Grasshopper is always optimum. Because you skip type checking and type conversion that David Rutten has implemented inside its components. But well, I can understand that scripting inside of Grasshopper is kind of losing all the graphical programming paradigm. Yeah, okay, that makes sense. This implies that all the components, the native Grasshopper components, are slower because at the beginning, at the start of the component, before it does any processing, any actual action, it's checking the type, which is slow, and yeah, that makes sense. Sorry if I'm bothering. No, I actually asked you to write me, so that's fine. Grasshopper in Rhino 6 has parallel computing built in many components. Yeah, we started with that. That was my first recommendation. As far as I know, you can never avoid typecasting. It's only hidden in Python and thus slower. Typecasting, it depends how it's done. Maybe, I don't know how it's done in the native components, but in Python, you natively don't really have types in Python, so it just crashes if you can have type hints, which are optional, but I think Python just crashes if you insert wrong data type. So that's it, and that's actually quite a good solution. It's just yeah, lazy function will not consume too much memory. That I've said that. That's true. Just input is well. That's a discussion about data types. Yeah. See. Okay. So it seems like that's all from the Facebook thread, and this already takes 2.5 hours, and I'm kind of tired of shouting into the microphone. So I think that's it. Hopefully this was helpful. The video will be posted on Facebook immediately when we finish. So I think it's going to be available immediately. But also I'm going to post it on the on our website, which is www.rese-arch.org. It's also in the name of this in the description of this video. Please have a look. We have a lot of stuff there. I don't mind if you don't buy anything. Just have a look. Maybe come up with some recommendation. What would you like to see? I'm certainly going to make one tutorial for Um, yeah. Also, Nader says that the precision algorithm is posted, so it's somewhere on the Facebook when we were discussing the integers and the precision of floating point numbers. You can have a look there. I'm very happy that people are contributing. I would like to thank to everybody who is contributing, and also please carry on. Also add more tips into this document. This is going to remain public, but also on Facebook or somewhere. Let me know what sort of tutorials would you like to see on our website, because we have around, I'm not really sure, but I think there are like 50 tutorials already. Not only for Grasshopper, there is also a set of tutorials for V-Ray, for 3ds Max, for the previous V-Ray version, and there is something I made for processing and generally creative coding. This is like an introduction that is applicable to also different programming languages, and I took a lot of effort to make this actually quite well organized and well made, so please have a look. I'm certainly going to make a tutorial for the data tree processing that I've shown a little bit today, and also I'm going to make a tutorial for the squid, which is again the Squid is a plugin by Mateusz Wierzicki, who also made a lot of other plugins, and it's very useful because I used it to create most of the animations that we made at our office recently. We also made some animated maps. We also made the tower that I was posting recently. That was not meant to be published, but the client was quite happy with it. You have probably seen the animation. It's being posted here as well. And it was quite useful for the client because I could show to the client how the actual tower that I was that we were animating. We were making an animation for an actual tower in the city, and this is how I was showing them it will look when they run it on the facade. And this is completely generated in Squid, made by Mateusz Wierzicki, who looks significantly similar to Alan Turing, who is here accidentally. Also, I made this animation for this tutorial in Squid. So it's incredibly useful. I don't know how many people are actually using it, but I wish more people were using it, because it allows you to save PNG files directly out of Grasshopper, and you can actually define them quite well as a set of instructions. So this is going to be quite nice. Okay, thank you very much. Thank you for the attention. Hopefully it wasn't too boring for you, and let me know. Give me some feedback. I'd love to have a feedback. Also on the website, the video is going to be in higher quality because Facebook doesn't allow for a higher resolution. So maybe it will be worth watching on our website. Okay, have a nice evening. Let me know. Let's keep in touch. Thank you very much. Bye-bye.